Okay, we've got two more examples here that we're going to try. For this first one that we're going to do, I'm not actually going to evaluate the integral, but I want to set it up. And what I want to do is set it up in two different ways. So you could have thought about in the last one as well, how did we know to pick dy first versus dx first? And truth be told, we didn't know. It didn't really matter. We had a choice in the matter. So we're going to see that in this example. And then if you want, you can practice it in the other one. If you want to try this example before looking at the solution, definitely feel free. Just pause the video and then restart it when you're ready to check in. The first thing I'm going to do is define that region R. So we'll get in this habit. So looking at it in the three-dimensional version, I've got my region R down below. Now, you can imagine that this picture was either already provided for you or that you could sketch it if you want. You might have done that with the help of some 3D graphing services, but regardless, basically we're trying to find the volume under z equals 4 minus y squared. That's that kind of paraboloid surface on the top, bounded by y equals 2, y equals x, and x equals 0. So we've got that region down on the bottom there. Now what I want to do, and what you should always get in the habit of, is we're going to draw our region R. So it's always a good habit to do this, to draw your region R, because it will help you find your bounds. So when we draw R, it's in the xy plane, and what we need to do is we need to look at the three-dimensional picture and kind of picture the 2D xy plane and tilt it up into the correct orientation. So I want to look for some of those key lines that we saw in here. So we've got y equals x, so I'm going to literally draw in y equals x, which is a line. We're going to draw in y equals 2, which is a horizontal line. And then we've got x equals 0, which, remember, x equals 0 is really the y-axis. So if we look at, we need to be bounded by y equals x, y equals 2, and x equals 0. This triangle defines my region R that we wanted. So now what we need to do is we need to take a look at that region and decide, well, how do I want to define it? What will those bounds be? So again, you're going to take a look at it and you're going to try and think about, which do you see first? Do you see a top curve, bottom curve, or do you see a right curve, left curve? Now, with something as simple as a triangular region, really in particular, one's not easier than the other. It's just a matter of seeding which one you see first, or potentially deciding based on the integral that we set up. And we'll see that in the next example. But so taking a look at this, let's suppose that we see top curve, bottom curve first. So meaning we're looking for function bounds for y. So looking at y, okay, what's the bottom curve and then what's the top curve, right? What's the lowest and then the top? Now in this one, the bottom curve is really the slanted line. It would be this line, which is y equals x. So y literally equals x. So the lower bound for y is x, and then the upper bound would be the horizontal line y equals 2. So y is going to go from x to 2. Now what we would need to do is we would need to look at numerically then for y going from x to 2, where does that happen on the x-axis? So what is the lowest that we want x to go, and what is the highest that we want x to go? Well, the lowest we want x to be, if we look on the x-axis, is over here at x equals 0. And then the highest we want x to go would be over here, so it would be, well, what's the x-coordinate of this intercept point? And this is the point 2, 2. So over here on the x-axis is a 2. So x goes from 0 to 2. And then these would be the bounds for my integral. So one way to define the integral is to do volume is going to be this double integral. Notice we're under the surface. The surface in this case was 4 minus y squared. And then we're doing this we chose to do dy first and then dx. And the bounds for y, we went from x to 2, right? We went from this line to this line. And then x goes from 0 to 2. Those were, x was, the smallest x coordinate was 0, the largest x coordinate was 2. So this integral would give me the value. It would be a perfectly good way to set it up. But it's not the only way to set it up. So we could instead try and look at this as a right curve, left curve scenario. So we could instead look at functions of x in terms of y and think about function bounds for x first that will still define the same region. So if I look at this in terms of right curve, left curve, well, moving left to right, the region really starts with this vertical line right here, which if we think about as a function of x, that's the line x equals 0. And then it comes over to the slanted line, which is x equals y. So really, x goes from 0 to y from this line to this line. And then to figure out, well, on that region, what are the bounds that I want for the y's? So kind of what's the lowest point and what's the highest point? So on the y-axis, that would go from here, from the origin, which is 0, up to the highest point of that rectangle, which is y equals 2. So notice we went from left curve, y equals 0, to right curve, x equals 0 to right curve, x equals y. So x went from 0 to y. And then on that, y numerically went from 0 is the smallest y coordinate to 2 is the largest y coordinate. It defines the exact same triangular region. Both of these sets define R. So it would be perfectly valid to also define the volume as being the double integral of 4 minus y squared. This time it would be dx first and then dy. The x bounds we chose were from 0 to y, and then the y bounds were from 0 to 2. Notice when you actually integrate those, the process is going to look different, because when I integrate 4 minus y squared with respect to y, I get a different result than when I integrate it with respect to x, which might make you think that we're not going to get the same result. But notice the bounds we're plugging in are also different. So we're not going to go through it in this video, but you all can practice doing both of those, do each of them, and you'll see that you get the same result in the end, which we should, because they both define a volume that's a unique volume. It shouldn't be variable. So they both will give you the volume under that surface, which is pretty cool. So really, we have some choice, we have some freedom in terms of determining our order of integration, but we have to be consistent throughout that full choice. In this particular example, it doesn't really make a difference, right? No matter which way I do, doing this dx, well, everything's a constant, just include the x's and then plug things in. It would be easy enough to integrate. Same here if it's dy. Well, we'd get something like 4y minus y cubed over 3. Again, plug things in. You easily get something in terms of x that's integratable. So, no problems there. Let's, though, try this next example. So again, if you want, definitely feel free. It's written up here. We want to try and find the volume bounded by. They phrased it a little bit different in this question, so they bounded it by surfaces for all of it. So bounded by f of x is e to the negative x squared, which is this top surface. Z equals 0, which is the xy plane. Y equals 0, which is the xz plane, right? It's this guy. Y equals x, which is kind of this flat plane that cuts right there. And then x equals 1, which again is kind of this front plane. If you want to try and set it up, definitely go for it. Pause the video and jump back in a second, but we're going to jump in. Again, my first thing that we need to do is we need to draw our region R because we need to be able to figure out our bounds. So I always want you to do this step of drawing R. So in this case, again, we look at that XY plane. We need in here y equals x again, which is this guy. We need y equals 0, which is the x-axis, and we need x equals 1, which is a vertical line. So if we think about it, right, we're bounded by y equals x, by y equals 0, and by x equals 1. We're getting this lower triangular portion is our region R. So again, we have to think through, well, how do we want to define this region? So, taking a look at it, again, as a triangular region, it doesn't necessarily seem simpler one way or another in terms of top curve, bottom curve, or right curve, left curve. So, one of the things we might think about is let's look at the function that we have to integrate. In this case, our function that we're going to have to integrate, if we think about what our volume is going to be, well, it's a double integral, but it's a double integral of e to the negative x squared. And if I think about needing to do that integral, e to the negative x squared doesn't have an elementary antiderivative if I do dx first. So notice we're going to do this over the region R dA. But notice, if I choose this to be e to the negative x squared dx dy, whatever these bounds are, even though the bounds themselves are pretty easy to find, so this would be something to something, something to something. If I try and take the antiderivative, I don't have an elementary antiderivative, right? For something like e to a function of x, you would use something like u substitution probably, or you might try and do product rule or any of those things. If I think about u substitution here, well, my u would be that negative x squared, but then my du would have to be a negative 2x dx, and I don't have an x dx, so it's not going to work out. And if I think about trying to do something like integration by parts, I'm sorry, I think I said product rule before. Maybe I said that in the other one too. We'll all figure it out. When I try and do integration by parts, well, I don't have enough parts particularly to do this. So if we think about this, this is not easy, but if I just switch the order to e to the negative x squared dy first and then dx, well, in terms of y, e to the negative x squared, the whole thing's just a constant. So when we integrate it, it's just going to be e to the negative x squared times y. And then we'll plug things in from there. So that gives me a little bit of a clue that I would prefer this order, which tells me that when I'm looking at my region, I want to do function bounds for y and numeric bounds for x, if they're easy enough to find, which they will be with this region. So let's do that. Function bounds for y means we're looking top bottom. Bottom curve seems to be the x-axis, so that's y equals 0. Top curve seems to be y equals x, right? We go from here to here. So y is going to go from 0 to x, and then we look at on that x-axis, what's the smallest x point and the largest x point. So it seems to go from 0 to x equals 1. What we've got then is we would go from y equals 0 to x, and then x is going to go from 0 to 1. Now, just as a note, right, if we were choosing left curve, right curve, be careful that x as a left curve doesn't start at the y-axis, right? My region doesn't start here, it starts here. So if I were doing this, my x bounds would be going from this horizontal, this slanted line of x equals y. We would start at y and then go over to 1. So we would go from y to 1 for x, and then on the y-axis, point to point, we would go 0 to, this is the point 1, 1. So we would come up to 0, 1 on the y-axis. So those would be the x dx dy bounds, but we're just not choosing it. It's hard to integrate, so we're going to choose something that's easier to integrate. Let's do a couple of the steps, and then I'll let you pause the video and try and finish it while I get the board erased. But taking a look at this, like we said, e to the negative x squared with respect to y is a constant. So then we really just have the integral from 0 to 1. We'll have e to the negative x squared y. We'll evaluate that from 0 to x. And all of that is still dx. So we've done the part of the integral. So we'll have the integral from 0 to 1. I plug in x. I'm going to move it to the front just to write it as x. And then e to the negative x squared. Plugging in 0 to y just gives me 0, so we don't have another piece. And then we'll do this dx. So why don't you pause the video for a second here and try and finish out that integral. Think back to our integration techniques to see what you're going to need to finish it. But it is a single variable integral at this point. So I'm going to pause my video as well and get this board erased, and we'll jump back in 1 second. Okay, hopefully you've got this finished already, but if not, we'll jump in together. Now, you probably thought about either one of two things. Probably first we think about checking u substitution, and if that doesn't work, then we probably do integration by parts. But nicely, with this one, if we think about a u substitution, well, u would probably be the function inside of the exponential, which is that negative x squared. That makes du negative 2x dx, and I do indeed have this x dx, which is perfect. So notice we've got like a composition of a function where the derivative of that inside function is a part of the integrand, so we don't need to do anything except u substitution. We'll move the negative 2 over, so really we have du over negative 2 is x dx. Let's go ahead and just change our bounds so that we don't have to worry about them. So our bounds, we had 0. So we had x equals 0, so now we'll have u equals negative 0 squared, which is still 0. And then we had x is 1, which then negative x squared is going to mean that u is negative 1. Now remember to keep those in their proper order. So really we have the integral from 0 to my upper bound is now negative 1. The x dx becomes du and a negative 1/2. And then e to the negative x squared just becomes e to the u. The integral of e to the u is e to the u. So luckily we just have negative 1/2 e to the u. We're going to evaluate that from 0 to negative 1, plugging in negative 1 first because it's the upper bound. So we have negative 1/2 e to the negative 1, and then we have minus negative 1/2 e to the 0. Cleaning that up, we get negative 1 over 2e, and then we'll really have plus 1/2 because e to the 0 is 1. So negative 1 over 2e plus 1/2 would be our volume. And if you do check it out, negative 1 over 2e is smaller than 1/2. So this is a positive value. So our volume does make sense. So as we saw in these two examples, you do often have some choice between whether to do dy or dx, depending on your region. Sometimes one is genuinely based on the region easier than another, the same way that we did back with areas, where sometimes it's just a lot easier to look at right curve, left curve versus top curve, bottom curve, because potentially based on the region, something like your top curve might change at some point, which would mean you'd have to split up the integral into multiple integrals. So it might save you that, but we also might make the choice based on this simplification of integration. We're gonna try one more type of example next, where we're gonna look at what if my region doesn't go all the way down into the XY plane. So we'll take a look at what that looks like. We'll jump back on here in another video.